$14 million from federal and $7 million from Illinois State to build the pilot facility. And here is the view of our center, about 4 acres on the campus of SIUE. So since we were created as an R&D unit for the coin to ethanol industry in 2003, since for the first couple of years, we've done a lot of R&D work, introducing innovative technologies to the corn to ethanol industry. Right now, we have about 200 ethanol plants in this country. Not only this industry provide the ethanol for the gasoline usage in this country, we also export ethanol and also the co-products as animal feed. So through NSERC, we've helped with a lot of technology development. So after a couple of years, we realized not only we are able to do ethanol as a fuel, we are actually also able to do a lot more. So since about 2009, we kind of turned the pilot facility into retrofitting the corn to ethanol industry to make a lot more other fuels and bioproduct. So through all the experience, we summarize here the major work we do. So in general, we actually conduct contractual projects, sponsored projects. We also do our own research. In addition to all that, we actually do, because we're on the campus of a university, we're quite good with workforce training as well. Not only working with a 4-year university, we've worked very closely with 2-year community colleges as well. So the next couple of slides, I'm going to go through each aspect in detail. So overall, in terms of the customer service, we're very proud that the past 20 years, we've been able to work for our clients on engineering design, method development, process control, and automation. One thing we really, our clients like it a lot is we respect our client's IP. So we only provide the service and the client takes all their IP. So in general, our team, we have scientists, we have engineers, we have operators, we also have business people. It's a very decent, small, but a very experienced team in the past 20 years. So this slide just shows we're actually in the middle of the Corn Belt. We call about 30 minutes from the international airport in St. Louis. So in the future, if you get any chance nearby, please come to visit us, look at our pilot facility. So anyway, so of course, the highlight, usually when we talk about NSERC, we want to talk about the pilot plant. So the pilot plant originally was pretty much a mini dry grind ethanol plant. So because of that, we actually have 4 22,000 liter fermenters, which were designed for anaerobic fermentation, for yeast fermentation mostly. And because of the dry grind facility, we actually, in the past decade also, we actually turned those retrofit to do a lot of other development, engineering, and for other processing. That's one of the things we are very proud we've done. For example, this fall, for the distillation unit, because we do fuels, we actually used our distillation to make butanol in the past. And this fall, we are going to actually help an international company to do probably the first time here to make not only ethanol, at the same time, make a green chemical as well. So we're trying to help the international company to bring the technology to United States. Things like that. We've done a lot for the modules we have from the dry grind ethanol plant. We utilize those for a lot of other chemical processing. That's one of the things our clients have enjoyed. For example, just this whole facility, we worked with one of the biggest chemical companies in the whole world, in the past 10 years, they brought some ideas, lab scale to NSERC. So as part of the open innovation platform, we helped them from lab scale, go all the way until today. We're still running today. Every year they come back trying to modify and process a biopolymer production. And that's one of the great example of retrofit according to ethanol production, making biopolymer. That's what we've done as well. So in addition to the pilot facility, we also have a fermentation suite. So I'm very glad that some of our fermentation team members are able to, in the attendees listening to this presentation. It's because of all those experts we have, engineers, scientists, and operators all together. They've done lots of projects for different clients. We actually also collaborate with the deputies team in the past as well. We were lucky last year. Illinois State actually gave us a wet lab expansion funding. So right now we are looking at very soon, we are going to, in addition to have a 30-liter, we're going to have 2 more 40 liters, 1 more 150 liter, and with the existing 1500 liter, those are pharmaceutical grade bioreactors. We've used those reactors for working with different clients, mostly fuel and ag products. That's what we've done. So here are a lot of details. I'm a chemist, so my colleagues, the fermentation scientists and the engineers in the audience, they came up with all the details about what we can do. So usually for us, when we have a collaborator or potential client, we go through details of talking about their projects, what their needs. Most of the time aerobic, and sometimes we also do anaerobic as well at a firm suite project. So we also, in addition to do contractual projects, sponsored projects, we also do our own research. So the Firm Lab actually became one of the most active places for our own research development. So at the Firm Lab, we actually have a lot of Flask incubators run Flask. Those you can do a lot of replicates, come up with statistic sound data. We have 1 liter. We also have 2 5 liters. So the interesting thing is a lot of the clients, when they do tech transfer, we usually, no matter how big size they want to try at NSERC, we always bring them to start from the 5 liter, make sure the NSERC team are comfortable with what we see, we can agree with what they've seen in their lab before we take it to the firm suite or the pilot plant. One of the things I'm very proud, I'm actually going to talk a little more, is one of the research projects we've developed with our postdoc, Dr. Minjun Ma, and Dr. Jay Dong, who used to be a postdoc at JBay. So this team, we developed something I call cellulosic sugar and ethanol library. So we've been working on this for about 2 to 3 years. So what we've done is we've screened various of waste material. The focus is on the carbohydrates in different kind of waste material. And specifically, we are only interested in bring low cost, low temperature pre-treatment method to convert those carbohydrates to sugars, then to ethanol or any other bioproducts. So far, we've screened a certain waste material. I'm going to share some with you later in my presentation. And we're also very actively in talking with various private industry people with different waste material to try. Also, we talked with Idaho National Lab. We like to work with them as well with their very enriched collection of biomass material. So that's about our Firm Lab. The last thing is about our analytical lab. So the analytical lab the number one job is serve as a quality control lab for the pilot plant. So we usually staff people with 24/7 when the pilot plant or firm suite is running 24/7. During downtime, we actually do a lot of our own method development as well. And we're very lucky, not only we do routine testing, we're also able to do, we've done actually a lot of high-level, in-depth analytical method development for the corn to ethanol industry and beyond. So that's one of the things we are very proud of ourselves with the analytical lab. So I'm going to switch the gear and talk about, so one of the goals for this presentation is I'm not only interested in trying to find partners, collaborators, utilize our facility. I'm as excited to want to share with this new technology we developed. So here I just want to share with a few pictures of what we've done. When we screen various waste material, the one stood out, performed the best was actually the landfill bound organic, landfill bound municipal solid waste material. So what we find out is through room temperature, low cost chemical pre-treatment, and the standard enzymatic hydrolysis, we were able to convert most of the carbohydrates into sugar stream. Not only we find out that we've already used the sugar stream to make ethanol, make a different kind of bioproducts, and the results were very, very promising. Because of that, we've worked with some of our collaborators, because some of the technology we help, the fermentation was based on synthetic media. After we tried their strain in the MSW sugar stream, we saw very promising results. So we worked together in the middle of trying to get more funding to help them. So in addition to municipal solid waste, the sugar stream, we find out using room temperature, working on corn stove is another way to do conversion on agricultural waste material. So here, what we do is we usually start with the screening from flask level. After we figure out the conditions, we actually go to the 1 liter size, going to do the room temperature pre-treatment, low cost chemical, low concentration of a chemical, and then we take the material to, we already scaled, we have a whole setup to 100 liter size for pre-treatment and enzymatic hydrolysis, then go to fermentation, connection with our firm suite. So here, just show you a few examples. So just want a few more. I did not put more technical because this is for scale up facility share. So I just want to let you know for corn stove, because I know a lot of other facilities have done beautiful job on corn stove. So when you use NCirc's room temperature, pre-treatment and enzymatic hydrolysis at about 50 C. So the conversion of sugars was not over 90%. So it was about 70 to 80% conversion on the sugars. So just want to let you know, but MSW was quite good. That's from our result. In addition to those waste, we also test the hemp biomass, which was quite good as well. When we tried orchard waste from California, and the challenge was high when we even raised the temperature to 90 C. Because my goal for our team, we know a lot of other beautiful technology can go over 100 C, but we just want to have a niche, like our focus on 90 C. So the orchard waste was actually hard. The conversion so far, what I got at 90 C was probably about 30% to 40%. So what we are trying to do for the hardy woody biomass, we are thinking to work with the thermal conversion team to trying to see whether we can do a fraction to take a certain part of the woody biomass for biochemical conversion using our method, but the rest of it going through thermal conversion. So that's a new area I'm trying to put a team together and to explore. So this is part of our research. So this one slide, actually I stole, this is our bench top research slide. So this is a tribute. I'm going to spend 2 minutes here because I see I still got time. So this is a tribute I want to pay to my colleagues from JBay, colleagues from ABPDU. So since 2017, since I became the research director at NSERC, we've worked with JBay and ABPDU for a lot of collaboration ideas, which helped NSERC a lot. So not only helped us with ideas, technology, you guys also helped us to provide a greater talent. That's Dr. Jay Dong. So Jay was a postdoc I learned, get to know when I was working with JBay. And he became assistant professor at our campus. Also, he holds joint position at NSERC as a fermentation scientist. So I'm very happy to see since 2018, Jay from JBay came over to NSERC and SIUE. He has landed about almost $1 million grant, research grant from the DOE, from USDA, from NSF. So to me, that's a great example of collaboration, of helping each other, and helping each other is a long term. And now I'm very enjoying. So this is one of the slides Jay is using to get his tenure check. I'm very sure SIUE and NSERC can't wait to hold him and not let him to leave and help to turn him into a tenure professor. But this is this lists all the different kind of research project he either already got funded or he's in the middle of working with multiple collaborators in this country trying to get funded. So let's see. This is the last slide. So like I said, to NSERC, because we have a pilot facility, we know it is a very, very good resource to do workforce training. So because of that, a few years ago, NSERC was lucky to land a $10 million US Department of Labor training grant, working with multiple community colleges in Illinois and beyond. So through that, we had a lot of students came over to NSERC, long or short, to get hands-on experience. We really used them as part of the workforce to deliver various projects, of course, under the full-time people supervision. So because of that, that experience enriched their resume and helped them to see the real world. They realize the work they do at NSERC is very, very different from all the work they've done across the campus, from the lab, from different facilities over there. So we're very proud to share with you, pretty much all the students left NSERC had no problem finding employment in the past decade or longer. We actually have a long list of extremely outstanding established professionals started from NSERC. So I think that's all I got. This is my contact info, and we'll be very happy to look for more collaborators. And hopefully we're very active. The scientists are active writing proposals. At the same time, the business team and the technical team are very busy talking with potential clients and all the good activities. Thank you very much for your time.
Thank you, Yan, for the great presentation. So everyone, I'm Ning, a staff scientist from ABPDU. I'll be monitor the Q&A box. If you have any question, please put in. We do have one question from the audience. Do you provide clients with insights into cell metabolism using computational modeling to improve fermentation process?
I can't speak for the fermentation scientists. However, I think in general, I actually call ourselves more applied, doing more applied science. What we do is we usually take established technology from bench level. We do a tech transfer. What we do the best is when we do the trials, we observe, we study the parameters, we correlate those to the yields. Then we provide all the processing parameters and the analytical data to help the client to figure out. And so it's a team effort. So it's a long way to tell you, we actually focus on more of the parameters testing around the clock and get feedback for the client. And a lot of times the client come over to see the process, like your team came here before COVID. So it's like that. And that's pretty much the majority of what we do.
Great. Okay, I have a question, Ian. I know you guys are located in university. You speak a little bit about how GA is holding a joint position, but in general, how do you work with the professor, the faculty in the university, and do you work also with the students?
Great question. Actually, let's talk about students first. So personally, I have benefit. I can't say enough how grateful I am for all the students I've had since 2004. So it's amazing how smart students are if you gave them opportunities. So it's a win-win. It's thirsty from both sides. So in SynCreo, you guys know, we only full-time people, we only have about between 15 to 20. Every time when we have a mega project, we need a lot of students. So yes, and for under Jay, and me as well, we've had several master thesis students. So for them, they stay with us. They stay with one project for 2 years. So that's one way. A lot of times, students will only come over summertime or over 2 or 3 semesters. So those are different experiences. That's on students' part. We truly both win from there. On the professor's side, I want to tell you, we actually, I realized that we actually interact more with students than with professors. The reason is we actually, our campus don't have a chemical engineering. We don't have bioengineering either. So it's more mechanical engineer, industrial and civil. So there's not a whole of overlap. The chemistry, yes. Actually, on the analytical side, we have a lot. So some of the students I oversaw for master thesis from chemistry were all on the analytical testing side. So it depends on the area.
Got it. Thank you. All right. Any other questions from the audience?
Ning, I might have one.
Sure.
So Jan, I was really appreciative of you mentioning the TACT grant, and I've seen that in other contexts in manufacturing. I was curious if you've given any thought to things like apprenticeships or even stackable certificates, which is a sort of a buzzword of late in manufacturing, training, workforce kinds of realms. Any thoughts on that?
James, that's actually a great question. So the one who owned that grant is my colleague, Courtney Brankridge. She actually, right now, she works not at SynCreo anymore. She works for the SIUE. Part of her job is actually watching that. So she, since that $10 million grant, she's been like Canon nonstop. So she's actually very active in that area with Illinois State and beyond. I know every year around her, she was like a magnet with a lot of professors. So they've got funding from USDA, all the other, and so that part, because I'm so busy with the research part, so that's actually not an area. But if any of you have any questions related to that, I can easily send to her, and she's an expert in this.
Okay, great.
All right, I don't see a question on the chat, so I'll ask the last question probably, Yan.
Yeah.
I'm really amazed to see the MSW work you are doing. So I'm wondering whether you can give a little bit detail, like what kind of substrate, what kind of municipal solid waste are you using for your, conversion?
Yeah, great question. So now I'm going to, how much time do I have? Oh, okay. So I have to be quick. So I tell you, we've got a lot of data. You're gonna laugh at this. Actually, out of a household trash, it was so hard to actually get MSW samples, research samples. It's almost impossible. But I'm very glad. Actually, I talked to INL recently. I think they're very good at helping everybody. So I feel like I'm better now. But all the research I've done, it's a long way to tell you, it's a household trash. But the results are fabulous because we did again using students. So we did actually, you were kind of inspiration for me a few years ago talking about your work. I quote your work every time. So we actually did a manual sorting. So we did all the mass balance. And after sorting, we did all the mass balance. So all the research are research grade MSW. So based on the results, I'm actually very confident. Even with large variations, I'm a chemist, and me is also a chemist, with a large variation, because the chemistry mechanism is the same. So I'm very confident it's going to work.
Great. I'm looking forward to see it in public.
Thank you.
All right. I think, yeah, with just one more minute, I'll leave it back to you, James.
Okay. So for those of you who are joining for this last session, who may have not been privy to the kind of introductory remarks that we offered before, I'll just mention briefly that we're conducting this kind of scale up facilities expo, excuse me, to really educate the community and really respond to the kinds of requests from ABPDU's collaborators as to more knowledge as for these kinds of capabilities throughout the country. And so it's fantastic to hear both nationally as well as internationally from a variety of facilities and a variety of capabilities, and so we're here to provide that forum for the community. This event really focuses on technical education of those capabilities, and as such, we will not be answering any business related questions at this time. It's really meant to be very much focused on that sort of educational piece. And so if there are technical questions that fall into the R&D category that involve potential IP, the speakers may not be able to answer them in this public forum. So with that, I will, let's see, turn it over to our next speaker.
All right, thank you so much, James and Dipti, for inviting us to give this presentation. My name is Owe Wang, CTO and co-founder of Pow.bio. We are a Berkeley, California-based company that provides intelligent fermentation services to the growing synthetic biology industry. We help other companies to validate their strains, to optimize their fermentation process, and help them to produce the first gram to kilograms amount of product. As a company, we also have a strong tradition in internal R&D with a focus on continuous fermentation, and hence today's title, The Future of Biomanufacturing. Although we talk a lot about our CMO capability, we believe the biggest problem in the industry is actually the cost of good. More and bigger bioreactor are not the answer. We actually need more efficient bioreactor technology and more innovation in the bioreactor space. We think the biggest problem in synthetic biology is that fundamentally everything is too expensive and too difficult to compete with their traditional part in the market. And this cost of good problem is fundamentally rooted in the traditional manufacturing mode, which is batch or fed batch fermentation. So if you think about batch and fed batch fermentation is slow, repetitive, and serial in nature. So every time you want to produce something, you need to set up the reactor, grow your cells, make the product, and take down, harvest the reactor. Repeat this process over and over and over. This process is extremely inefficient, and there's a lot of downtime and results in low volumetric productivity. Alternatively, what we could do is continuous fermentation, in which 24/7 you have a material that cheap raw material that continuously get transferred into the bioreactor and that get transformed into value-added product. So 24/7, this process is online. It results in multifold increase in volumetric productivity. It drastically reduction in capex and OpEx because you no longer need massive reactors or massive production campus. And this process also operates in steady state and therefore drastically allows automation and drastically reduce the OpEx. Here is a snapshot of our TEA analysis just to show that our technology can decrease capex on new site by 75%. So basically here we're showing the traditional fed batch system versus the continuous Pow.bio's continuous fermentation platform. When we're aiming for the same productivity or production a year, which is 10 kilotons a year, the investment for fed batch facility that is required is about 187 million, versus for a continuous facility is only about 40 million. The cost of good is also reduced by about 50% as well. And I'll share a little more about our TA in some later slides as well. You may wonder, if continuous fermentation is this great, why we don't see more continuous fermentation in the industry? Why I would say 99.9% of the facility out there are fed batch facility. That is really because continuous fermentation has three major obstacles or technical challenges that really prohibit deployment of continuous fermentation in the wider industry. The first problem is contamination. So unlike fed batch system, continuous is an open system. So 24/7, you can have a dust, a spore somehow fall into a reactor, and that quickly just kills everything. The second problem is the problem of mutation. So continuous fermentation, again, is effectively a direct evolution experiment. So over time, the continuous reactor, the strengths in the continuous reactor will evolve for a increase in biomass yield and decrease in product yield, because effectively they try to tear down the production pathway. You know, they're not our friend. They don't want to make product for us. They just want to grow. And then the third problem is the problem of optimization. So continuous fermentation in general is more complicated than fed batch, and because it runs for lengthy, there's usually a continuous reactor runs for 2 to 3 weeks, and because of that, it's very difficult to allocate and find enough tank time to really effectively optimize a continuous system. So these three problems fundamentally stopped wider adaptation of continuous reactor in the industry. And we at Pow developed a platform technology really to solve these technical challenges and really provide a platform continuous technology that is generalizable, work with diverse range of microbial host and product classes. With our technology, which I'm gonna talk about in the next few slides, we use a 2-chamber system as the hardware to solve the contamination and the mutation problem. We build a self-optimizing fermenter as a software to solve for the optimization problem. And these two technologies, which then really translate and transform the cost of good and to bring down the cost of production, which will share our techno-economic analysis. Our patent technology runs reconvert this continuous fermentation system into efficient and predictable ways. I think there is a problem with the video if I'm not crazy. Yep, the video is not showing, which is totally, which is okay. I think the fundamental aim of our setup, which is supposed to show in here, is to separate growth and the production. So basically, we are operating a two-chamber system in which there is separated by a growth chamber and the production chamber. In the growth chamber, the idea is that on the growth chamber, which is usually on the left of the schematics, the idea of the growth chamber is to continuously generate biomass. And then the idea of the biomass, the idea of this growth chamber is to continue, it's basically a continuous propagation chamber and continuously generate biomass into the next chamber, which is the production chamber. And in the production chamber, the idea is that we want to continuously produce product without any biomass growth. The second production chamber does still receive feed. So the cells effectively are in a zombified state. They continuously receive glucose feed, but they do not grow. And because they do not grow, the cells, the system, the biocatalysts are extremely resilient toward contamination and mutation. There is also a tangential flow filtration system in which we use that to continuously recycle the cells, the active biomass, into the production chamber and continuously extract the product. And then lastly, there is a drain line, which is basically a bleed line that we can use to control the biomass retention time in the production chamber and to avoid cell fatigue. So it's much easier if there is a schematics, obviously, but please feel free to reach out. I'm more than happy to share that figure just to show you really what is the mechanism we use to control for mutation and contamination. The whole idea with this system is really that in the growth chamber, because there is no product formation, there is no selective pressure for the cells to lose its production pathway, and therefore the system is very robust, right? You don't have to deal with like direct evolution to evolve for loss of pathways because the pathway never turns on. And then in the second production chamber, because we do not have any product, we don't have any growth, even if it's contaminated or if the cell mutated, which when the cell mutated is effectively a contaminant, there's no way for this mutant to sweep and outcompete all the bioreactors to sweep the productive biocatalyst in the system. So with that, here you just have to, without saying our schematics, you have to believe me that we have a very robust and functional system. So here is a really proof of example of or like kind of demonstration of how the system will work in real life. So on the left, we are showing a cumulative production of mevalonic acid over time. So this is the E. coli mesophilic process, and it's also genetically assembled process, right? GMO host. So we are not like relying on any extreme conditions to ensure this process operates. Basically, in a single round of continuous fermentation, we generated 1 kilogram amount of product, as shown in the pink line, versus over the same time period, the feedback process only made little more than 200 grams, showing that our process results in 5-fold increase in productivity. Of note, this is not a kind of weak or like a random process that we picked to make us look greater. This process is actually a commercialized and a highly optimized process. We also not shown here for the sake of time, but we also achieved a similar result with a PKI protein production system as well. So next, we actually scaled up our process in-house and at ABPDU. So on the left, again, we're showing cumulative product over time. The dashed lines, so the black dashed lines and the gray dashed lines are predictions, basically what projected product over time. So basically, we took our data from the last slide and multiplied by a scale factor, and therefore projected it into 15 and 10-liter scale. So in this blue line, which is what happened in-house, we basically, as you can see that our cumulative product over time overlays fairly well with our projection. And in this red line, this is actually operated at ABPDU and carried out by Eric Sandstrom, Laura Fernandez, and Johnny Dong, really to help us to validate that our process can be independently reproduced in a different site, so that our process is not that finicky, right? Our process is actually can travel at different sites. Thanks for the heart. I don't know. And on the right-hand side, we're showing overall volumetric productivity. So basically, as you can see that for all three runs, that the overall volumetric productivity ranged around 1.5 to 2 gram per liter per hour, which is much higher than the traditional fed batch, which is about 0.3-0.5 gram per liter per hour. And we are in the process of scaling up this process to the 300 liter with the aim to scale this up to 1,000 liter this year. On the next slide, so we're gonna change the gear a little bit and talk about fed batch again, and talk about optimization. So optimization in a fed batch system, again, it is a very slow, repetitive, and serial in nature. Each bioreactor is effectively a giant test tube. So you basically spend a week, kind of take care of it, give it a lot of love, and hope that after a week, it will give you one set of data. So 1 week, 1 tank generate one set of fermentation result. On the other hand, we could also carry out the same optimization process, but in a continuous manner. So what we can do is set up a continuous reactor, let it reach steady state, and continuously perturb the reactor so that we move to different fermentation conditions and then look for the output. So as illustrated here on the upper right, these are real data. On the pink line and then the white line are basically fermentation input, and each orange bar represents a different condition. So over time, we changed the input condition. You can see the pink line and then the white line changes over time, and then the output, which in this case is carbon evolution rate. So the DO and carbon evolution rate. So the blue line and the green lines changes over time. And the result is summarized at the figure below. So basically you can see as we change pH and temperature, the carbon evolution rate also goes up and down. Carbon evolution rate in our system is a proxy for growth rate because it just, as it's happier, grow faster, you need more feed and emit more CO2. With this system, it really set the stage for the next layer of work. So what we did is that we then evaluated the 50 different numerical optimization algorithms. We also looked at the different flavors of reinforcement learning algorithm and aim to identify which algorithm that is best suitable for this continuous optimization workflow. So an early example is shown here. So this is elder meat optimization algorithm in which it does basically this is a response surface map, and this algorithm does 3 different actions: a reflect, expand, and contract, and to search for its most optimal position in this response surface map. We took this algorithm and basically translated that into executable code that can speak with our SCADA system to automatically drive our reactor. So what on the right is effectively real life data. So basically our researcher associate inoculate a reactor and then click go, and then the reactor automatically change the pH and temperature. So that's the two axes, the X and Y axis, and search for a higher and higher carbon evolution rate. So that's the Z axis, that's the height. So as you could see, the basically the algorithm automatically searched for an optimal position. So almost like self-driving car, but this is a self-driving reactor. And then there is no reason for us to just stop at pH and temperature. In addition to pH and temperature, we can also scan for growth rate, carbon flux, nitrogen flux, DO or respiration quotient, and instead of just growth and CER, we can also look for titer, productivity, and yield or product yield, biomass yield, and things that really drives changes production economy. So here is another example of a process that coming through our continuous optimization pipeline. We are showing pre and post optimization and basically showing titer changes pre and post the optimization. You can see a 5 to 10-fold increase in titer improvement, depends on which metric we're looking at. This process also result in, our process also result in 33% increase in productivity. Of note, this process was a feedback process. It came in as a feedback process. We optimized the process in the continuous platform and then use that knowledge that learned and translate it back into a feedback process. So just saying that once we go through a feedback optimization platform, we're not really married to a continuous process. You can just you can always go back to a feedback system. Why does this matters? Because with our technology, this is really the first biomanufacturing platform to unlock cost parity at scale for a commodity product. We have two technologies. So the first is the two-chamber continuous bioreactor system. And with that, we deliver 5 to 8-fold higher volumetric productivity. The benefit of that is to really generate more stuff from a smaller bioreactor, and with the cost implication of reducing the capex by 75%. The second technology, which we call SUFI, self-optimizing fermenter, actively control and optimize the process in real time in a continuous bioreactor. And therefore, fewer in actual setup, fewer people need to maintain and intervene the process. It also automatically search and optimize the process and really fully evaluate the process and search for the ceiling of the bio process instead of just using some boilerplate conditions or unoptimized process in bioreactor, as just because we all know that there's never enough time to optimize the process. So why do you work with us? In the end of the day, as I mentioned earlier, we are a intelligent fermentation provider. We are a CDMO. So we solve for scale up speed and cost, right? You want to work with us at a smaller scale to scale up faster. We want to accelerate your process of development by 5 to 10x times. And you want to work with us at a larger scale to produce more product for less money. And with our technology, this really translates to 5 times increase in productivity and therefore translate to 50 to 80% reduction in capex and opex. Here are two scenarios of our techno-economic, just generated from our techno-economic analysis. We kind of shared the upper scenarios already. So basically, when aiming for the same productivity of 10 kilotons a year, with our continuous platforms, this translates to 78% reduction in capex and 2-fold lower in cost of goods. In the lower scenario, in which basically we're saying, hey, oh wait, I only have $25 million to spend. What can we do? Well, we can only afford about the same reactor, that is 50 cubic meters. The productivity in continuous is increased by 8-fold, whereas the cost of good is reduced by 4-fold, just because, again, fundamentally, continuous is a much more efficient process. There is minimal downtime, there is minimal takedown and setup, and you don't have to go through repetitive biomass growth phase as well. The process is always like we effectively freeze the process in a productive state and therefore continuously generating product. Our technology ultimately enables novel bioproducts to get to market more quickly and profitably. In this gray line, basically showing a legacy approach that usually takes about 7.5 years to the first sale. As you know, SynBio is a very it's not an easy process. It takes a very long time to really commercialize a product. However, with our technology, our aim is really to accelerate your product to market by years and really accelerate your time to revenue. Our technology can accelerate the process development and generate material for rapid prototyping at gram to kilogram scale. We have two offerings. So one is our process development service. With that, we leverage our hardware and software to improve your build process. This is really for leadership looking for solution to reduce time to market and to increase the speed to revenue. And with this process, you provide strain and assay. We work to meet pre-planned milestones and you pay for results. So it's a milestone-based engagement. In the second offering, which is the bench to pilot material generation, we generate the amount of material you need when you need it. And this is really for teams that need material without waiting for 6+ months to get into a CMO. And in this workflow, you provide strains, process, and assay. We generate the material you need, and you pay per gram to kilogram. What are some technical requirements? Obviously, this platform, although it's a generalizable platform, it still has some requirement. From the left column, E. coli, Pichia, Bacillus would be a strong technical fit for the project. It would be especially beneficial if your product is toxic because we control for titer in our system, as well as if your product is extracellular. Excuse me. For bioprocess, we strongly prefer inducible process. We prefer defined media with glucose or typical carbon feed. And you do need to have an assay. If there's no assay, unfortunately, we cannot really help the process just because having analytical capability, like having a platform for common ground of truth is really important for CMO work. And then some potential technical fit, basically all other yeast and bacteria, intracellular product or biomass, constitutive systems, and if you need some downstream DSP process such as spray drying. Not a fit, things that are not a fit include unstable strains, filamentous fungi, plant mammalian cells, BSL2 or higher, just because we're not in a facility to offer this kind of services. Cannot be toxic product to humans. It's okay if it's toxic to bacteria. We don't do gaseous product just because we don't have that capability. Unfortunately, we do not do anaerobic or gas fermentation or processing. It requires extreme enrichment. We do not work with solid state solid media, or we don't work with a large amount of methanol, just again because of safety configurations. And you must have an assay, as I mentioned earlier. So with that, we are also committed to partner and developing the next generation of biomanufacturing leaders. So on the left column is our work with Professor Jason Ryder at UC Berkeley and his students is visiting our facility, and we also went out to UC Berkeley to the poster sessions that hosted by Professor Jason Ryder. On the right column, we have Professor Doug Bruce's class at Linnaeus College. And Doug actually work as a visiting professor at Pow as well. And every year we receive a few interns from both university and the colleges. And the interns, after they work at Pow, they usually continue to pursue higher education or convert them to a full-time research associate. We are also actively share our technical advances with the community, and just because we believe collaboration is very essential to the future of success of SynBio. So here on the left is me presenting at the SMB just last week, and Brian Lee, our COO, presenting at a different SMB earlier this year, and our CEO Shannon Hall presenting at SynBio Beta. And here's our team. We are a Berkeley, California-based company. We have 2 sites. Both are in Emerald, Berkeley area. We are proud of our team's diverse identities. We think the world needs of us to build a better future. And with that, just want to mention that we're always looking for clients, collaborators. So if you have questions, please do not hesitate to reach out. Thank you so much for your time.
Okay. Fantastic, Owe. All right, are there any questions at this time?
Yes, we do have one question from the audience. So always the question is, the mechanism of the two-chamber system sounds very interesting. How do you envision this going to a commercial scale with your client? Would your client have to build their own facility, or are there existing CMOs that can adapt their facility to your technology? Or do you offer a large scale for biomanufacturing?
Yeah, that's a great question. There are many layers to the question as well. I think the first question is all our hardwares are currently off the shelf. So we're not a hardware company and we're not developing our unique hardwares. We do develop our unique softwares. So with that regards, we do expect most large scale CMOs should be compatible with our continuous technology, or at least that's when we design our process, that's what we have in mind. We know there are large-scale CMOs, Fermic in Mexico, as an example, tested continuous fermentation with not super optimized results, but we know they can do it. And hopefully they can do it robustly with the two-chamber setup. And our longer term vision is definitely building our own large scale facility to carry out continuous fermentation, and as well as working with our clients in terms of potential licensing or joint venture terms to build large scale continuous manufacturing facility.
Thank you. Any other questions? Oh wait, I have a quick question. So you mentioned about obstacles to convert a batch fermentation process to a continuous. So based your experience, what's the most challenging step when you try to convert a batch process to a continuous fermentation process?
Yeah, that's a great question. I think the challenge come into multiple different flavors. I think the most typical problem we have seen is just not well-developed feedback process, or like unscalable feedback process, or processes that are extremely unstable. Although our system is I would say resilient toward genetic drift, but because in many 2-liter feedback processes, it doesn't require the process to go to that many generations. In a 2-liter feedback process, maybe the strain is stable for 25-30 generations, which is decent enough for that workflow, but the strain is just not advanced enough for any continuous or even just large scale work for as part of their seed expansion. So I would say that is unscalable process and underperforming strains are the 2 things we have observed in the past.
Got it. Thank you.
Great question.
We do have one more question from the audience. Do you see more cell lysis from shared stress from your tangential flow filtration and any increase in peptides or amino acids?
That is a great question. TFF is definitely major, maybe not concern, but something we work super carefully, just making sure that we're building our processes not handicapped by the TFF capability. We actually run the TFF. Our filtration rate is very small, so we run them with pretty low transmembrane pressure, and the overall pressure is also very low. So we don't have the problem of major like cell sharing or lysis with the TFF. We also scaled our TFF accordingly, kind of watch the scale up factor over TFF. So we scale up the process to make sure that our TFF we can scale, right? It's not like an unscalable process, almost like a magic trick at 2-liter scale, and you cannot go to cubic meter scale. So that's definitely something we are working very carefully. We do not monitor amino acid, release of amino acid in our system, but I do think that's a great idea just to monitor as a way to monitor cell lysis potentially. So great question.
All right, thank you, Wei, for the great talk and answer to the questions. We don't have any more in the chat.
Great, thank you, Nate.
Okay. Hi, everybody. Thank you so much to the ABPDU team for facilitating. This has been so inspiring. Thanks to all of the other presenters today. My name is Karen Warner. I'm with an organization called Beam Circular, based in Modesto, California, so the agricultural heartland of California. We are a nonprofit organization that is backboning a significant regional public-private partnership and initiative working to grow an ecosystem around the circular bioeconomy. That ecosystem is going to be anchored in a really significant innovation campus right here in the Ag Heartland, right next door to the Bay Area. And that innovation campus will have a significant shared testbed facility that I'm excited to share a little bit more about. So jumping right in, our mission as Beam Circular, we'll see if I can get these slides working with me. There we go. So we're really focused on unlocking the incredible power of agricultural communities like this one to transform waste into opportunity through the circular bioeconomy. And we really think about opportunity both in terms of environmental and climate solutions, as well as the tremendous amount of economic opportunity and inclusion and equity that we can build in communities like this one by bringing really high quality jobs in the bioindustry to regions like this. We are pursuing, I'm getting a little bit of a lag, so forgive the delay. There we go. So we're focused on pursuing this mission by accelerating and helping to scale up innovations in bioindustrial manufacturing. And we're taking a really big tent approach to defining this industry, really looking at the full range of food and industrial applications in biomanufacturing, everything that's outside of pharma. And when we think about feedstocks, which is really core to what we're focused on here with Beam, we're talking about conventional feedstocks as well as the really broad world of circular and sustainable kind of emerging or future feedstocks. We have some images here representing some of the most significant feedstocks we have in great abundance here in the North San Joaquin Valley, from grape pomace, from our winemaking industry, to almond hulls, shells, and orchard waste, certainly lots of different types of woody biomass, as well as a broad range of food, fruit, vegetable, and other types of agricultural residues. We are interested in energy and fuels as well as food applications, agricultural, industrial, chemical materials, really big tent of kind of end products. And then we're currently really technology agnostic, but thinking about the many different ways that place and the ecosystem around this industry can really help to support in accelerating the most promising solutions by thinking about an aligned talent pipeline and workforce system, the different types of enabling infrastructure that is necessary for this industry, local, state, federal investment, as well as a really supportive supply chain, and thinking through the factors upstream and downstream that can help to support the advancement of these activities. The Beam initiative is sort of how we think about our portfolio of work. Beam stands for Bioeconomy, Agriculture, and Manufacturing. We have a very significant and ambitious portfolio of projects and strategies that were developed out of an inclusive economic development planning process with advisors from the Brookings Institution, who are experts in industry cluster development, as well as a tremendous set of advisors and industry experts from across the country and the world. We have, as part of this portfolio, a number of interventions related to advancing innovation, again, infrastructure, talent, access to capital, and then a number of cross-cutting initiatives. That includes the launch of CBio Collaborative, which is the name of a National Science Foundation Innovation Engine Development Award recipient. We are a coalition of partners co-led by Lawrence Berkeley National Laboratory, the ABPDU team, Beam Circular, and UC Merced, alongside a growing ecosystem of over 30 cross-sector partners who are looking at ways to really intentionally support the development of this ecosystem. So I'm going to chat just a little bit about our region, and then I'm going to get into more specifics about the shared testbed facility and our vision for that innovation campus. So we're based here in the North San Joaquin Valley. This is the heart of the most productive agricultural region in the most productive agricultural state in the United States. The North San Joaquin Valley includes San Joaquin, Stanislaus, and Merced. If you're familiar with California, the big cities are Stockton, Modesto, and Merced in this region. We are the next door neighbors of the San Francisco Bay Area. Over 90,000 people commute every single day from our region to the Bay Area. So this is a commuting distance region to a global hub of biotechnology and obviously general startup and innovation resources. In our Tri-County region alone, we produce 30% of the almonds consumed in the United States. 100% of the almonds consumed in the US are produced here in the San Joaquin Valley. We also have tremendous abundance of fruit and tree and other specialty crops, as well as traditional energy crops, and certainly large livestock and dairy producers as well here in this region. California is the most crop diverse state in the country, and we have an enormous both abundance and diversity of the types of agricultural residues that are produced here in our region, which we think makes this region really specially well suited to lead in innovation as it relates to future and innovative and emerging feedstocks. We also, as mentioned, are right next door, not only the Bay Area, we are in the center of the Sacramento and the South San Joaquin Valley region, so the other kind of mega powerhouse agricultural engines of California. And we are next door to and part of the supply chain flow for the Eastern Sierras, which is a heavily forested region in our state. And certainly the state of California is very eager to make use of the woody biomass out of that region as well as a wildfire management strategy. We did some really exciting, kind of interesting analysis of the regions around the United States that really validated how unique this particular North San Joaquin Valley region is. In this map of the US, we've filtered for the top ag producing counties in the country, and then looked where there are counties that are both the top ag producers and leaders in manufacturing activity. And these blue shaded counties are the only 5 places in the country that have the combination of large scale ag and a leading concentration of manufacturing activity happening in the same place. We are one of those places. And the reason that we are a leader in both of these is that not only do we have tremendous volumes of ag production coming out of this region, we are global leaders in food manufacturing and food processing. So we have tremendous amounts of adjacent and relevant complementary workforce assets, infrastructure, supply chain connections, but also an additional source of really interesting feedstocks for the bioindustrial manufacturing sector. We're the only one of these blue regions where you have large scale ag and high concentration of manufacturing that is also right next to one of these beautiful orange stars, which represent superstar tech hubs in this country. So again, that adjacency to where we have this concentration of innovation, not only frankly in the Bay Area, but also north of us in Sacramento and the UC Davis area, we're right next to innovation, and we have this tremendously well-suited location for adjacency to feedstock and ability to scale up manufacturing. So we are really excited about taking advantage of this opportunity to help accelerate the scale up of innovations in this sector, as well as bring home environmental solutions and again, economic opportunities for our region. I won't go into tremendous detail, but happy to nerd out with anyone who's interested about our variety of crops and some of the sources of biomass and feedstock in this region that's particular to the North San Joaquin Valley. One way that I like to think about it is that if you can innovate with the biomass here, you get relevant solutions for places all around the country and the globe. As mentioned, we are global leaders in food processing. So it's not just that we have a lot of this activity, we have many of the largest individual operations in various food sectors in the world based here. E&J Gallo Winery is based in Modesto, about 10 minutes from where I'm talking to you now. Hilmar Cheese, Blue Diamond, across a number of different food sectors, we have tremendous global leaders in food manufacturing already based here in this region. So as we think about Beam Circular's focus and our role in the ecosystem, we're particularly focused on scale up and helping to bridge that valley of death, getting folks out of the bench and pilot scale up into demo and commercial scale activities. We have ABPDU here as reference, some of our close collaborators in this work. And then I want to get into kind of our focus today, of course, which is shared and contract manufacturing facilities. As part of that portfolio that I mentioned, we are looking at an anchor asset for this ecosystem being development of a very significant innovation campus. We're looking to co-locate scale up and demo facility capacity with commercial scale activity. So we are thinking about this as a campus. And this shared commercial scale facility is going to help firms to move again from lab-based viability to commercial manufacturing. We're going to be anchored by an estimated 20 to 25,000 liters of fermentation capacity with multiple bioreactors, upstream, downstream processing capabilities, and analytical tools. We are really focused on being strategically designed for flexibility and again for this feedstock diversity. We want to have the capabilities and the ability to help folks scale kind of conventional feedstock solutions, but also be really focused on the ways that we can move into additional kind of diversified sources of feedstock for different products. We are going to include food grade as well as biomass conversion facilities. The goals, as we think about kind of the goals of this campus, as well as this shared testbed facility, kind of think about these in three buckets. We think about wanting to have direct impact on industry and really supporting kind of catalytic advancements of solutions in this space. We think about delivery of meaningful impact on the local community that surrounds this operation and future operations that may be modeled after this one. And we think about impact on environment and hopefully advancing the most promising solutions for climate and other environmental challenges. Our design partner that's been engaged in this first phase of development of the facility is Nextrong Technology. They have over 200 years of cumulative experience supporting over 100 clients with successful projects, and they are really aligned with our mission in terms of both industry delivery of results as well as sustainability goals. So we are currently at this phase in the conceptual design phase, so I'm just going to be giving you some really high level notes here on kind of our current status of how we are envisioning this. We're about to wrap up our FEL 0 or conceptual design phase and are moving into FEL 1. We are at this point envisioning that we will have traditional feedstock storage in what we're calling our foundational platform space. The feedstock traditionally seen as waste streams or are featured more in what we're calling our emerging platform, which we're thinking about that including, of course, not only woody biomass, but a really broad range of agricultural residues as well. These aren't black and white categories, but really more about thinking, helping us think about where there is emerging equipment, kind of technology readiness of the equipment itself versus use of really established mature equipment for scale up of new technologies. The facility will feature 4 main fermentation halls, conventional food grade, conventional for fuels and chemicals, gas fermentation, and cellular agriculture, with space for alternative fermenter designs. The facility will also feature shared and specialty downstream processing equipment for each fermentation hall, as well as some shared equipment, if applicable, to more than one area. The facility, as I mentioned, will feature food grade and food innovation platform, as well as food processing equipment. And then finally, we are situating this as part of a broader innovation campus. So we're really excited about exploring a variety of partnership opportunities, as well as anchor tenants who could be interesting co-location partners for commercial scale activities, as well as relevant upstream and downstream activities. As I don't have a timer up for me, and I know we started a little bit late, so please, James or Deepti, jump in if you need to cut me off. I just have a couple more here if we have time.
Okay, go for it.
Okay, so I won't spend a lot of time here, but just to give kind of a sense of how we're thinking about this foundational and emerging aspects of the different technologies that we're hoping to support. And again, this isn't about black and white. There's folks that may kind of fit into different categories, but the goal here is really to note that we are looking to be supportive of emerging processing equipment and technologies, as well as the scale up of technologies with more conventional feedstocks and equipment. And waiting on my slide delay. So a little note on progress and where we're at. We have raised over $15 million since Beam's launch in January. That includes a really significant commitment from Stanislaus County, our anchor local government partner, of $10 million to seed our initiative. As mentioned, we're an NSF Engines Development Award recipient. We've received pilot funding from the state of California and are just beginning kind of our private sector raise. This is really a very big picture public-private partnership that is evolving here, and we've been really excited to see significant early momentum, including commitment from local partners to make this happen. This is our growing network of leadership council members who are part of that collaborative I mentioned, who are all really in various ways supporting and engaging the development of this ecosystem, from local government to state government, the state California Department of Food and Agriculture, Governor's Office of Business Development and Economic Development, as well as California Department of Conservation, have been really wonderful early partners in this work. Industry, workforce development and education, and community partners all on board to really, again, think about this as a holistic ecosystem. Our core leadership team and set of initial advisors include our partners from ABPDU, Deepti and James, who are here today and are part of the co-lead team from CBio Collaborative, Ann Veneman, the former U.S. Secretary of Food and Agriculture, as well as a number of advisors, both from the UC system, from Brookings Institution, Almond Board of California, and really a growing network of folks and advisors who aren't represented here. We are super excited, this is a lovely little quote from a CDFA Secretary, Karen Ross, about hopefully the meaning of this engine and this opportunity for rural communities. This is a fabulous pile of almond hulls at one of our local hullers and shellers to think about one of the many sources of biomass that we're looking to leverage here in this region. And then please take a screenshot because I won't keep this up for very long, but we are very eager for your feedback. So as mentioned, we are in the conceptual design phase. We are still iterating very much on the specifics as we continue to move into FEL1 for this testbed facility. And we would love to hear from you. So if you are a firm that is exploring scale up capacity, there is a link here, bit.ly, it got cut off a little bit, but it's Beam testbed, or here is a QR code to fill out a little survey. Would really, really welcome any of your input. And would be great to hear from you about your priorities as you're thinking about the capacity that you need. And then finally, here's my contact information. Incredibly grateful for this chance to share. And we are really jazzed. Again, I heard people earlier today say we don't want to reinvent the wheel. We agree. We want to learn from all of you. We want to be filling gaps. We want to be complementary to other efforts in this space domestically and globally to scale this incredibly important sector, and are looking forward to hearing from you, hopefully, about collaboration opportunities. So thanks so much.
Great, thank you, Karen. Maybe we can take one question, James, due to the sake of time. So, Karen, we have a few questions in the Q&A. Maybe you can type the answer after this. And we have one more from the panel, from Yan. The question is, how do you plan to collect the waste feedstocks in your region, sorting them and transporting to the processing facility you are planning to build?
Yeah, great question. The short answer is in many different ways. So we are engaging in a number of interventions that are supporting the overall supply chain development. That includes specific opportunities for the many different players that plug into this supply chain. We also, as part of our portfolio, are making investments in certain shared strategic infrastructure, depots and other things that will enable kind of the more of a consolidated approach to feedstock supply. But we know that this isn't one answer. This is really about nurturing and developing an overall supply chain. And fortunately, a lot of that is already really ready to be leveraged here in this region because of how advanced our food logistics and agricultural supply chain is, and the number of players in distribution and storage, and the number of different things that go into moving biomass around a region. Thanks.
Okay, thank you. My name is Xiaoshan Xiong. I'm from the MicroPort SynCreo Biotechnology. My base is in Shanghai, China. Actually, we are quite a young company. This is our first time to make a presentation in public. So it's really great timing, right? So my title is Build an Ecosystem for Synthetic Biology-Based Manufacturing, because we look at the synthetic biology is kind of a systematic workflow. As a startup, how can we first do a great R&D and also build the manufacture facility and further provide service with our community? This is our purpose. So first, I just briefly introduce our team members. As I said, my name is Xia Chao. I just came back to US and to China last September and joined the company. I have a long experience in synthetic biology and manufacturing engineering. Before working here, I was an assistant professor at Washington University and also served as a CTO and director at different companies. So the president is Qingwei Sun. He's from the MicroPort corporate. He oversees over 10 companies regarding the strategy and operation. He got his bachelor degree and master degree from Kyoto and Harvard University, respectively. We also have some senior members work on the fermentation, downstream processing, and construction. You can see here, these people have a lot of expertise in the engineering part. We have recruited more than 10 members, and further we'll grow the team. As I said, we have 2 locations. First one is in Shanghai. Actually, the MicroPort SynCreo is a part of the MicroPort corporate company, and then we acquired a company, Kerui Pharmaceutical in Fujian province. As we know, in Shanghai, it's very hard to build any manufacturing factory because of the cost, the environmental impact, and other factors. But in different areas, they have different advantages, right? So in Fujian provinces, we can see it's very close to the. It also is in the east-south area. One of the largest ports here, and we can do a lot of shipment by sea. So this can save a lot of cost in the future. And these 2 locations will bridge the gap between the R&D and manufacturing. I will introduce a little bit our R&D efforts, and also can provide this service with our community. First, we develop a very comprehensive set of synthetic biology tools. We use antigen yeast as a chassis. We build the EPRIM platform and advance the genome editing tools. We also have the capability to do the genome scale metabolic network modeling. We can carry out the metabolic flux analysis based on the silicarbon-13 labeling substrates, such as the glucose. So this can provide us the rational design strategy for strain engineering and build the cell factories. The product portfolio, I just list some here. We can produce lipid as biofuel and renewable chemicals. Some of the unusual fatty acids are really high value products. At the same time, we can expand the product portfolio to include some more to include lipid soluble products. We just talk about the DBTL, right? The cycle. The last one, we also we're building a very high throughput screening platform. In the past, the traditional bottleneck for the test is really low throughput and also labor intensive and time consuming. So we built a optical screening platform based on the spectrum imaging the cellular metabolite. It can do the in-situation analysis of cellular metabolites at a single cell level. And also it is high resolution measurement without fluorescent labeling, because basically we measure the molecular vibration, and also it's very sensitive and accurate. by further combination of the microfluidics sorting, we can do the basically the facts, but without the fluorescence labeling. So this is our manufacture facility at Fujian province. So we built this. This is in the chemical industry park. So it meets all the safety regulations. We have different areas, function areas, such as fermentation, downstream processing, and we know the fermentation will generate some waste, such as the wastewater. We have the wastewater treatment plants. We have the specific areas for the stock of the solvents. It kind of have a power supply and also warehouse. Of course, we have office areas. We also leave some areas for the phase 2 construction. Just within this 1 year, all of this facility almost available, and we can totally operate this one by the end of this year. So there is around 30 acres manufacturing plant. We can do the demo to large scale fermentation. Usually we have installed around 30 cubic meters fermenters here, and we'll also build the downstream processing capacity. The production lines compliant with the China, the United States, and the European Union GMP requirements. Because the company's name is pharmaceutical company, so in the past we majorly focus on the active pharmaceutical ingredients, but within the synthetic biology, we also can produce nutritional cosmetics and health products, and further include renewable chemicals. Other than we use this capability, we also can provide the service with our people. So this is how we look at the synthetic biology workflow. First, we can help us identify the target, the application, and what kind of a strategy. As I mentioned, we have the capability to do the metabolic flux analysis and further reconstitute the metabolic network. We have the genes library and also build the promoter libraries. We use some very unique microbiome as our host. We can do the whole different gene expression and also we can use the genome editing tools. The last one, we emphasize the precise fermentation and also downstream processing. So this is our commitment to the diversity, equity, and inclusion. The MicroPort SynCreo is very small and a new company, but the MicroPort corporate is kind of a large company in China. It has I think 6 IPO companies listed, and also our commitment is work from the community and for the work for the community, and also together with the community, we have provided a lot of support and resources such as education, medical, and other environmental protection. I'm quite new to this company, but I recognize this culture and I will enjoy work here. So I think that's major part for my presentation. Yeah. So if you have any questions, please go ahead. And also we are looking for any kind of collaborations, and your suggestion also will be welcome. Thank you.
Okay, fantastic. Thank you, Xiaozhao. Are there questions?
I don't see a question in the chat or Q&A box. Xiaozhao, I have one question on your online monitoring. So you mentioned the metabolite online monitoring you have developed. I'm wondering whether you can give a little bit more detail on that, like what kind of metabolites can you analyze and how?
Yeah, actually, it's based on the molecular vibration because we know, right, for the like raw of this, most of kind of we can monitor the structures, but it's really not sensitive, right? But with like Professor Sunny Xie's work, they can provide very accurate and sensitive measurements. But problem right now is that people still use like glass slides to check the metabolite. But we can right now we are using the microfluidics, and also we can measure it really within the single cells. And the metabolite usually we prefer like lipid or the and also like steroid like Xtero, because it has a lot of carbon, hydrogen. Then the structure will, then the singular will be stronger. The other one is we can use like clinical chemistry, right? Then we have a lot of functional groups here, but still need some kind of the design and further make it more easily to use is really hard. When we talk to the optical engineers, the change a lot of parameters. So this is very good, development, but it's not accepted by a larger audience. This is why we are here. Yeah.
Okay, thank you. We do have question from the audience about computational tools again. Have you had success with using computational tool in terms of improving yield and productivity?
Yes, we actually maybe we're at different levels. For example, if we talk about the flex culture, we use these tools, right? But if we talk about bioprocess economy, we have use different TI tools. For my experience, I majorly focus on the small scale culture. For example, we have the MFA, metabolic flux analysis. If we use lipid synthesis as an example, in the past we know SQA, NADPH, energy. All of this required to biosynthesize the lipids, but usually maybe one of these is the bottleneck. Then you will generate a lot of CO2 release. It decreases the carbon efficiency, but with these tools, we can better engineer the cells. And also, it's not only introduce the foreign genes, but we need to understand the metabolic flux and the network. So this is my short answer. Thank you.
Great, thank you. If you have any other questions, please put it in the chat in the Q&A box.
Thank you, James and DP and the team at ABPDU for giving us the opportunity to introduce Pow.bio at this expo. Looks like I've got the control. Thank you, James.
Yes.
Pow.bio is a business unit within Perfect Day. And Perfect Day itself was started in 2014 with a mission to change the process, not the food. We focused on precision fermentation derived dairy proteins to start off. And the idea being that we wanted to provide the same experience as dairy proteins in terms of functionality and taste and feel, and without the baggage associated with the current supply chains. So the vision driving our efforts was essentially moving the world towards a kinder, greener tomorrow. And to do this for the first set of proteins, which is primarily dairy proteins, we had to build a really strong R&D team to solve all the technological challenges along the way. We have a globally distributed R&D team with our headquarters in Berkeley. And we also have facilities in Logan, Utah, which is scheduled to move to Salt Lake City early next year, where we have research as well as piloting facilities. And we also have R&D facilities in Bangalore, India. So the genesis of Pow.bio itself from this mission of bringing precision fermentation derived dairy proteins to market was quite interesting. I think what we essentially realized as our first molecules were graduating from the R&D pipeline was that what we had built was a technology platform for protein expression. And all the technological challenges that we had solved for all the teams that we had built and infrastructure that we had developed, this was done through collaborations, including once with ABPDU. I remember the days when we had trekked over to ABPDU to run some of our bin scale fermentation and the pilot runs as well. So thanks to all of the partners, and we managed to solve something we think is of value. And given our desire, our vision to drive to a kind of greener tomorrow, we asked ourselves the question of how could we have the most impact given what we had built? And the answer was quite obvious to us at that point, that not all the best ideas for next molecules could come from within Perfect Day. And we wanted to open up what we had built, the ecosystem and the technology platform that we had built, to external partners to bring their visions to life. That's essentially what Nth.bio is set up to do. So Perfect Day itself is aligned into two distinct business units that operate more or less independendly. One is the Nth.bio business unit that I'm representing here at the Expo today, which is essentially offering up as service the technology platform infrastructure and the teams that we have built at Perfect Day to realize our first molecules. And the other part is the ingredient innovation team, which is focused on commercializing the molecules that we have already developed. So the way we treat customers and partners at Nth.bio is that there's no distinction between the internal ingredient innovation team, which is also treated as a customer or a partner, just on an equal footing with any external customer. So given this, I think the impact we'd like to have, like I mentioned, is through enabling our partners to realize bring their molecules to market faster through leveraging our technology platform. You could ask what the USP, what is it that differentiates Nth.bio from other service providers? And one of the things that we pride ourselves in, recombinant proteins are itself not new to the world. I think what we have done at Perfect Day and Nth.bio is that our claim to fame is we are the first player to bring precision fermentation derived heterologous commodity proteins to market at usage levels that accommodate food applications, I would say. And we have been commercial for almost four years. So we have a proven track record in terms of being able to produce product that's in the shelves across the country and also across the globe. And we are partnering with several multinational brands as well. So this brings with it what we have built. We think we have solved for a lot of the challenges regarding the ability to scale proteins, scale the production of proteins that open up new avenues for precision fermentation in terms of the scale and the cost that we are able to bring to table. So one other thing that we have tried to set when we are setting up Nth.bio, one of the learnings that we've had through our journey is that R&D itself is, we are all very familiar being scientists, that it's not very linear. And the facets involved, the pipeline involved to bring a product to commercialization is long and involves is a cross-disciplinary effort involving multiple teams. And having a seamless integration of this all the way from strain engineering through your process development teams and taking it all the way to manufacturing, having that be a seamless venture is quite important to maximize the chances of success and also accelerate the timeline. So the way we set up programs at Nth.bio is learning from all of this experience of what it took us to get to commercialization. And that's something that we offer to the partners to bring their ideas to life. That being said, I think the platform itself that we have built is very specific to proteins. So we have developed a suite of host systems, primarily filamentous fungi and single cell yeast that we can use for protein expression that are proven at the manufacturing scale. And our process development philosophy, we've heard quite a few interesting talks during this expo as well about some of the frontiers of where the manufacturing in this area is heading to. but we also recognize that to be at a commercial level early, we also need the ability to leverage existing infrastructure as well. So both have a foot in the future as well as in the present, in a sense. So in terms of the process development philosophy, having that the dual modality where we are working on cutting edge as well as being able to slot our processes into existing technologies, that's very important to have, to be able to be commercially viable. And in this process, I think the one other key aspect that usually it's very important to have very early on in the thought process and in our minds as we do the R&D is the regulatory efforts and scalability. So this is, as the sooner you have this as part of your operating philosophy, I think the higher the likelihood of successes. And this is something that we pride ourselves as in our DNA at Nth.bio. Having said that, the end-to-end strain to scale programs are set up for proteins, expression of proteins, production of proteins. We've deliberately chosen to invest into excess capacity, where we've typically run into bottlenecks ourselves when running internal programs. This is in fermentation, bench scale fermentation capacity, piloting capacity, and manufacturing capacity. So these are three buckets which are, in addition to the strain to scale programs, are available for partners as standalone services as well. So this was a deliberate choice made because this is a bottleneck that we ourselves are trying to solve for. And if there are perhaps even non-protein related work that you would like to do where you're looking for capacity, these are some things that we also have available in a standalone fashion. I mean, I would like to keep the talk short. The rest of the slides are primarily elaborating on the strain to scale slide that we presented here, and I'm open it up for questions and any discussions. I think we'd love to hear from partners who are looking to accelerate your path to market in collaboration with us, and would like to bring your ideas to fruition. I will just skip through this. I'm hoping that this slide deck will be shared. So this was just for completeness sake that the slides were included. But yeah, I mean, yeah, I'm happy to take any questions, and please feel free to connect. And we'd love to hear what you have going on and how we can enable you either through our standalone services or our end-to-end services for protein expression.
Okay, fantastic. We can dwell on this slide for a good little while. We have several minutes for Q&A.
Yeah, just once again, the reminder, if you have any questions, please put it in the Q&A box. So far, I don't see the question. I can get started. My question is about the downstream processing. So when you scale up your process, like any of your fermentation process for the downstream, do you see the downstream processing more involved with scale, or you feel like it's at certain stage it's less challenging?
So it's a very important question. Downstream process is probably can add, depending on the choices you make quite early on, can add perhaps the most cost as well. And the choices in downstream process you make are very important. Like, I think it's important to keep in mind what the production cost you're targeting at the end determines the unit operations that you choose right from the development stage. That's very important. And the second thing is also in terms of some unit operations might be necessitated by some of your background. I mean, and it's like I mentioned, it's going to be a continuous process for the downstream feeding into your strain engineering to make it simpler. So I might not be answering your question exactly, but it depends. I think if you look at a purely yield basis, your DSP yields are typically a little better at production scale as compared to your bench scale. That's just because your you're not able to recycle material and stuff like that when you're running bench scale experiments. I don't know if that answers your questions, but it depends. It's very contextual in terms of what molecule you're working on and what scale you're operating in and what cost targets you're trying to hit.
Yeah, definitely. Yeah, because in our experience, if our generally our collaborator for downstream, they have pretty straightforward. If for small scale, it's easy, and but when they want to do a pilot scale, it might be challenging to develop a continuous process. So I'm wondering, yeah, after that stage at larger scale, whether the challenge still exists or it might be less challenging.
It's always going to exist because the kind of like when you're talking about scales of 250,000 liters, 500,000 liters, there's it's very hard to simulate some of the even from a metabolic perspective, the kind of gradients that the organisms see. Your whole background profile might be very different. That might not even be something that the bugs experience at a smaller pilot scale. So it's something that you have to constantly work towards, and there's models out there, scaled down models that you could use to simulate some of these sort of scale challenges to get a more representative broth that will help you de-risk a lot of your DSP. That's definitely a challenge, an ongoing challenge that you have to keep a very close watch on.
Great, thank you. We do have a question from the audience. Do you work with E. coli? Can you please mention some advantages of filamentous fungi for recombinant protein production?
Yeah, definitely. I think we don't work with E. coli primarily because the choice was made because of the economics of our first molecule. We are competing with commercial whey, and the cost at which it needs to be produced is in the tens of dollars is at most that we can produce. So E. coli, it's it's produced intracellularly, so makes downstream process challenging, expensive, and the yields are not high enough. Filamentous fungi are known to produce a tremendous amount of protein, and it's all secreted. So that's the reason for our choice of filamentous fungi. Yeah, I hope that answers your question. And it also depends on the choice of the host depends on multiple factors. I think we like Ning mentioned, downstream is a very important consideration when picking your host. Also the cost, the titers you need to get to, your productivity levels that you need to get to. And the last factor is also the timeline. Some hosts are easier to engineer. The development cycles for filamentous fungi are typically longer. So we make choices based on a multitude of these things, how fast we need to get to what metrics, what's the, at what cost will the molecule be commercially viable. That dictates, and what kind of DSP do we want, that kind of dictates a lot of the choices with regards to picking the host organism.
Thank you to our speakers once again. We do have one more question in the Q&A. Could you please answer them through typing, since we are running out of time? Yeah, if you have more question, please feel free to reach out to our speaker directly.
All right, thank you.
Thank you.
Okay, all right, so next up is Mehmet Tulbek.
Thank you very much, James. Good afternoon, everybody. My name is Mehmet Tulbek with Saskatchewan Food Industry Development Center. It's my pleasure to speak at this expo, and especially would like to express my sincere thanks to Deepti for having me in the last minute in the program. Saskatchewan Food Industry Development Center has been established in 1997 as a innovation and a development agency for primarily in Saskatchewan at that time, focusing more on the meat applications, fruit, vegetables. Over the last 25 years, the center has been significantly evolved and focusing on more crop, meat, plant-based foods and ingredients. We have over 60 full-time employees working at the center. The last 20 years, we helped develop and processed and commercialized over 1,000 food products, helped over 450 clients, and helping primarily in all the sectors in the food industry. It's organized as a not-for-profit incorporation So we are reporting to the Ministry of Agriculture and University of Saskatchewan and a board of directors, about 13, 14 board of directors. And I'm basically leading the organization within different programs. So if you look at some of the mandates we have, we basically do it with our 4 pillars. We're expanding, driving the innovation with primarily Saskatchewan agricultural inputs, but more Western Canadian, the more and more and development and processing of plant-based foods, helping supporting entrepreneurship, reducing capital risk, and support the commercialization of new technology, research and development. So we don't take any IP on the position of any project. We don't file any patents. We don't take any IP. So we run the project for the companies. We run the projects for the clients, and then whatever we run for them, they own the entire IP. It's a very similar organization, like almost like Las Vegas. Whatever happens here stays here. So it's very important for the clients to understand that. So that's why, like, how we drive the overall commercialization and the new technology and R&D. Going back to this click. So we are located in Saskatoon, but we are a global organization, especially the last 10 years, significantly increased our capabilities, helping clients all over the world, primarily in Canada, US, South America, as well as Europe, Middle East, Asia, Asia Pacific. And one of the reasons for that, Saskatoon has become a very well-known science and technology hub. We have AFC, NRC, several different institutes, the overall breeding programs for peas, lentils, fava beans, chickpeas. So when you look at the entire crop on the alternative protein from pulses to oil seeds, the primary canola production, canola processing region is Saskatchewan, Western Canada. Peas and lentils and fava beans and chickpeas. There's quite a bit of pulse production. Oats, the #1 production region. Spring wheat, Canadian wheat, durum wheat, the #1 production region. Mustard, flaxseed. When you look at the entire the variety, it's more than the corn and soybean. That's why there's quite a bit of knowledge and institutional base in the region with all the different development. So when we look at our programs, Food Center is focusing primarily on agri-food utilization, and around that we have product development, manufacturing and incubation, extrusion R&D. We have 3 extruders from 32 millimeter to 75 millimeter. We have food safety skills development, ingredient science technology, ingredient innovation, food grade crop quality. We have engineering, life cycle analysis, process authority services, abattoir inspection services. We have a women in agri-food entrepreneurship, women startup support, business advising group from BC to northern Quebec, all the way 8 provinces and territories supporting women-owned agri-food startups. And the last edition we have is the fermentation and bioengineering. It's a supplement and additional facility that we are supporting our clients. So if you look at what the Food Center has, we have 2 facilities, a pilot plant at university, about 10,000 square feet, Agri-Food Innovation Center, about 57,000 square feet, and adding the new fermentation and bioengineering facility, about 9,000 square feet. Now, in these facilities, we have CFI inspected, certified facilities. We can manufacture meat, dairy, processed foods, honey. This is also ASAP certified facilities. This facility, we also have BRC certification, plus. We have organic, halal, kosher. So the products that we can manufacture here can be sold into the marketplace from the Food Center. A wide variety of capabilities, over 200 pieces of equipment, and mostly on wheels, very flexible. We have trained operators, commercial manufacturing in both facilities, and 5 incubation suites. So there are like 5 to 10,000 square feet different incubation suites. The clients, they can rent the facility and manufacture their products. So these are also additional benefits for the industry in Canada. So what we are doing now, we just recently in the process of establishing our Advanced Food Ingredients Center. This will be primarily focusing on advanced ingredients and fermented and bioengineered ingredients. It's a separate facility in our premises, about 9,000 square feet. And the front part is done, working on some of the backside, and by the end of the year, we'll be fully commissioning the facility. And if you look at it, in this facility, we'll be serving as a contract research and a contract manufacturing organization. We'll be helping startup companies or SMEs or large-scale companies or multinationals to validate their processes at a scale to produce their advanced ingredients for new food applications. From ideation to commercialization, we'll be taking their journey, and then the infrastructure will have upstream and the downstream processing available. So if you look at the submerged liquid fermentation capabilities, from 1.5 liter, we have 2 10 liters, a 50 liter, a 75 liter, 150 liter, a 750 liter, and 2 10,000 liters. So basically, we are trying to take our clients from 1.5 liter up to 2 10,000 liters with the right downstream processing capability. In terms of the solid state, we are going to have a 5 kg, and we also have a 300 kilogram for primarily on the biomass and looking at different applications on the agri-food industry. There's that type of need by the industry that we've been getting quite a bit of questions. So we'll have 5 to 300 kilogram solid state fermentation capabilities as well. Now, in terms of downstream processing, we'll have a decanter with 2-phase and 3-phase centrifuge, disc stack centrifuges, filtration, micro, ultra, nano, pasteurization, and the drying capability. So we have a 200 kilogram spray dryer, a 25 kilogram spray dryer. And in terms of batch, we have convective air, fluidized bed, freeze dryer, vacuum tray, and microwave assisted vacuum drying technology. So in terms of the fermentation ecosystem initiative in Canada, we are leading this, promoting the use of Western Canadian plant-based products and the co-streams. When you look at the entire canola production and the crushing facilities and the new investments coming, there's quite a bit of canola meal, a lot of starches, fiber, co-products, byproducts, and we are helping the collaborations, partnerships, and support the training and education, the backbone for this fermentation industry to augment additional industry growth. So these are additional support we conduct. And the main programs are focused on, and these are really driven by our clients, from conventional like sourdoughs to tempehs, different food applications, to bacterial biomass such as probiotics, plant inoculants, to mycelial biomass, value-derived, and the precision agriculture such as cellular agriculture, synthetic biology, and everything is really driven by the clients for us. 90% of our work is confidential. About 10% work, we do some research for the universities or the ministry or different agencies around the country, but that's quite limited. So most of the work is really driven by the clients. We recently published a review paper about the fermentation-enabled food valorization potential, primarily looked at some bioengineered enzymes and precision fermentation industry. By utilizing this technology, we think that we can address so many different questions and the problems happening in Canada in terms of byproduct, raw products, different co-products, and as well as like a food waste, and looking at different applications from fermented products to food and feed to probiotics to reducing anti-nutritional factors, upcycling, bioactive compounds, several different programs. So, and then the main area for us is really not only to utilize this platform of fermentation and bioengineering and add it into the agri-food value chain with our expertise, with extrusion, product development from dairy, non-dairy, meat, non-meat, plant-based, extrusion, different forming technologies, ingredient innovation, manufacturing, and advanced food ingredient processing. So to tap into several different programs for the industry. One other support mechanism that we established is primarily the process engineering and advanced manufacturing for the companies around mainly for the process design, advanced manufacturing, data-driven process analytics, techno-economic analysis, and the life cycle analysis, primarily on the food miles, looking at the journey of a raw material from going one place to another process, taking the byproduct from taking one place to another. So there's quite a bit of sustainability story in that, which we are helping the clients and the industry as well. And really, this is the overall summary for the program. Really, in Canada, what we are looking at, there's quite a bit of startup activity supported by National Research Council, Natural Products Canada, Ontario Genomics in Bio, AgWest Bio Gap, and this is also supported through universities and gives several programs. So it's really one of the mechanisms that we can help these companies. And again, there's not that much really big, we are looking at 20,000 liter and hoping to add maybe 20,000-30,000 liter more. But again, when you look at the numbers, it's still a drop in the bucket, what we are seeing in North America, in US and Canada and other parts of the world. We need more of these activities. So our role will be more with the activities that we'll conduct here. It's going to be tapped into additional commercialization projects through extrusion or product development or other type of activities the food center can provide. So with that, it's basically trying to position the center as a one-stop shop from an idea to the finished product. And this is my email address and information about our food center website. And again, thanks so much, James, for the invitation. Look forward to the questions.
Excellent, Mehmet. Thank you so much. We have questions.
Okay, I can get started. I don't see questions from the audience yet. I'm wondering what's the size of your staffing team? Like what technical background do they typically have?
So we have PhDs in biotechnology, genomics, microbiology, PhD on food processing, ag biosystems engineering. I have PhD in cereal science, masters in food engineering. We have about 10 PhDs in staff. And on fermentation side, we have 2 PhDs, 2 masters, and 2 techs. We have about 6 people now. And trying to, again, this is not only the focus of the organization. This will be a really key focus of the organization with the fermentation bioengineering programs. We run about 150 projects a year, but from a product development, from fruits and vegetables to sausage processing, fermented flours, all these different products. But with the focus on the raw material, co-product utilization, the growth in the region, that's what we established. And we have the right teams and established expertise in the program, and look forward to receiving more clients.
Great. Also, Deepti has a question.
No, I wanted to point out that Yan has a question in the chat.
Oh, okay. Yeah, I got it. Okay. Yan's question is, are you interested in converting agriculture waste or processing waste to sugars and ethanol for industrial usage?
Yes, we have a couple of projects going on. We are looking at kind of an open innovation project right now, looking at a byproduct into biobutanol, supported by Ministry of Agriculture here. So we're interested in doing that type of work. If there is any interest collaboration, we'll be glad to talk to the members from the audience.
Great, thank you. Yeah, please follow up afterwards.
Thank you.
All right.
Thanks again. Thank you.
Thank you.
Okay. All right. So yeah, let's come back now to Ron Shigeta and Solar Biotech.
Hi, everyone. Solar Biotech is a synthetic biology CDMO type of startup. It's founded by industry veterans and now has recently expanded to some full capacity scaling facilities. I'm going to review today. I think the real thing that I want to sort of say is differentiating what makes Solar Bio special is that those of us who've sort of dug into it know that biotech has been an industrial powerhouse since the 70s, and a lot has happened in industry. Sometimes we're acclimated to sort of the advances of the technology that's been sort of done on the private side. And Solar Biotech is run by white biotech industry veterans who have launched dozens of products. And so it's quite a different slice of experience, which is really interesting. The facilities that I talk about, some of them have been operating for almost 3 years. We have a full certification for food. There's all these certifications, as well as the food certification for FSMA production of food and halal and kosher, as well as some of the other ones can be provided upon request. I think another thing that really differentiates us is that we, as a CDMO, we will help re-optimize your protocol. Sometimes you come out of a workhorse like ABPDU, scaling. Sometimes the protocol requires adjustment at each scale. But probably what's more important in terms of certification is to get your product cost of goods down. I think that we sometimes focus on fermentation a lot. Not that fermentation is not very, very important, but that the strain is obviously very important to your cost of goods. And the downstream is also, upstream and downstream processes are very important. And that kind of experience is sort of harder to find. And that's one of been Solar Biotech's niche, is sort of working on upstream and downstream scaling at the product scale and looking at the cost of goods that result from that. Right now, there are four operational geographies, sites that we have sort of put together to basically cover all kinds of interesting cases. France, the French hub is actually focused on animal cells, and that's more for cultured meat. They have a fairly large scale kitchen. They have scaled chicken cells there and produced meat. The original bioprocess development hub is in Norton, Virginia, which is the very western end of the state of Virginia. That is where the main headquarters is, as well as our Cincinnati site, which is mostly focused on intensive strain engineering. The bioprocess development hub at North Virginia can take your strains. We do have all the typical scales between 1 and 15, 40, 200, 800, and 10,000 liter scale there. We are really excited to announce the acquisition of a biomanufacturing hub in Ontario, Canada. Capacity is currently 160,000 liters, but the plans are to eventually expand it to 2 million liters. Just to sort of, here's some pictures of the Canadian site, formerly Noblegen, which was focused on algae growth. We're rapidly retrofitting those to sort of deal with any kind of fermentation host that you can imagine, as well as filamentous fungi and pichia and yeast and bacteria if that's necessary. We're really proud of Noblegen's, the acquisition of Noblegen's site. It's going to be expandable to, what we'd like to do is expand that to create manufacturing lines for startups in collaboration with you as a special collaboration. And to create these joint ventures, everybody could have a nominally own their own manufacturing line and sort of get the kinds of cost of goods that you need. And sometimes you can't get in manufacturing without a lot of consulting hours and long and difficult education. Here's some more slides of Noblegen. I'm going to sort of move past this to talk a little bit about the experience. So I think the best thing that we can say about Solar Bio and the things that we're most proud of the past few years is the actual taking of products to market. Our founder, Alex Berlin, has shipped scores of products at his time as a chief of development at Novozymes, the Ubli protein, some of the animal-free chicken food, bio oils, as well as Himami, which was Motif's heme product. It was actually meeting its cost of goods goals. There were other issues that happened there with Himami, but we're really proud to have actually gotten that to the point where they were ready to take it to market. And there's some biomaterials, lots of other, we've actually had about 10 or 12 customers we've taken to scale at commercial levels, contemporary synthetic biology products. This is I'm going to spend a little time on the Norton, Virginia site. It is also a very large, It's also a very large site. It has several thousand square feet of free area here to continue to grow the size of the tanks. On the left-hand side, you can see our gang. That's our 10,000 liter tank with a feeder of 4,000 liter coming in to 100 liter test facilities. We can actually do I think 8 simultaneous 800 liter fermentations there. And there are similar skids that run the 40 liter scales as well. And we have a lab. These are holding tanks. We have the hub there is really well designed. It has some of the cool things that a real food production facility needs. It has 2 loading docks, one for delivery of raw materials and another one to pick up the processed materials. Everything is very professionally sourced, and cell banking, everything is extremely efficient and to industry standards at the highest levels. Some more of our tank. CEO Alex Berlin actually supervised the construction of our first gang here personally. We have extensive downstream capacities that in most cases you'd have to rent separately and actually come into CDMO with knowledge on how to produce the downstream product. We will work with you to create that for those customers who can handle long-term commitments to the facility. Here's a couple more downstream. There's the centrifuge, and we actually, these on the left-hand side are, I think they're 30-foot long chromatography columns, if that's what you need to do. Of course, chromatography is incredibly expensive, so you better be making some sort of pharmaceutical grade product if you want to use one of these columns, or it better be incredibly powerful. But we can do almost anything, and we can sort of work very hard to get, we can actually meet your needs in terms of getting samples for your arrays and your diligence stack. We've done that a dozen times already. And then we can continue to work beyond that raise to get to the cost of goods that you want. Here's some more of our skids that we have here. And the facility's got quite a few. We actually have a very advanced facility that can sort of bring things up on skids and reconfigure the line in a relatively short period of time. So the development costs are relatively low for what you'd have to pay for yourself. The pieces of equipment we don't have, we have a wide variety of contractors that we can sort of put the finger on, arrange those facilities for you, and keep your costs low. This is the cell line, the animal cell production facility in France, for those who are interested in meat. We have collaborations with a couple of them. And here's some of our downstream capabilities in Canada. I think the idea would be to actually develop process to 10,000 liters and then move to large tanks. We have gangs of 20,000 liter tanks there that can be combined to reach scale at this point up to, like I said, 160,000 liters. But we can add more tanks very easily. And just some more eye candy here. We don't have on-site spray drying in Virginia. We generally prefer to sort of ship that to a contractor in North America and in the United States, but Canada does have some on site. And I'm really proud to work with the management team. They are, like I say, they're usually multiple decade veterans in biotech. They've shipped synthetic biology products, protein products by the ton, and scores of successful product launches. That experience has really been differentiated in terms of how quickly they can deliver, how accurately they can measure the expenses and the time. And they will work super hard to get everything done exactly when you need it. We have a great track record along those lines. And we have, I think this is the Canadian site right here. Our team is actually more like 20 or 25 people at this point. We can maintain, obviously we can maintain 24/7 shifts for weeks on end, and everything has a very consistent outcome. And that would be my presentation. At this point, I'm happy to take any questions. If anybody has any questions for me, I'll give you my email. And that's in the chat. So thanks for your time.
Excellent. Okay. Any questions?
Oh, thanks, DT.
If you have any questions, please type it in the Q&A box. I don't see any for now.
That's fine. It's 5 o'clock.
Yeah. Everyone getting tired. So thank you for staying with us. Ron, I have a quick question. So you show different sides for your company. I'm wondering, do they communicate closely or they kind of working independently?
Well, some of the units are quite different. So the French unit, I mean, there is pretty good communication, but the French unit working with animal cells and none of the other sites work with animal cells. That's much more, there isn't so much minute-to-minute conversation required. The Cincinnati team works on strains. And so that often is, that's actually preliminary to actually going to scaling projects or going to fermentations, you know. So I think that the Canadian site and the Virginia site will be handing off projects and interacting more directly. And of course, Alex is very involved in every project.
Thank you. Okay, I think we can move on. Back to you, James.
Thanks very much.
Thank you.
Right. Thanks again, Ron. All right, so we are about to wrap, but with one more presentation from yours truly. So ABPDU will provide our overview, and then I'll tack on some information to the end of this. Welcome to the Advanced Biofuels and Bioproduct Process Development Unit, ABPDU for short. We are a bioprocess scale-up facility located in Emeryville, California, adjacent to Berkeley, the hub of the synthetic biology industry. This overview describes the technical capabilities of the ABPDU and the ways in which collaborators leverage this publicly available resource. The ABPDU is funded by the Department of Energy's Bioenergy Technologies Office to support industry and academic partners, helping groups scale up technologies and develop prototype level product materials. This fisheye view of the ABPDU fermentation lab shows some of the facility's assortment of bioreactors, ranging in scale from 250 milliliters to 300 liters working volume. The ABPDU also offers over a dozen different recovery options and chemical catalysis reactors that can generate grams to kilograms of prototype material.
This is not just a deck of cards. This is a collection of 54 beautifully designed.
The ABPDU exists because technologies optimized in high throughput assays rarely scale up to the same performance level in bioreactors. Capillary effects in well plates, application of real-world feedstocks in bioreactors, or switching from batch to continuous modes are just some of the many reasons why process scale-up development is such an important part of biomanufacturing R&D and a common barrier to bioproduct commercialization. At the ABPDU, we like to say that we meet our collaborators where they are. If a new startup is looking for support to transform a shake flask technology, we have multiple bench scale options which we can use to develop a scalable process. If a company with a mature process is looking to execute on, say, a single 300-liter campaign followed by pilot scale recovery, we are happy to perform such projects as well. Similar to fermentation, we have several options available in feedstock deconstruction and chemical catalysis, from the 10 milliliter scale to hundreds of liters. Our partners have found these capabilities useful for both upstream deconstruction as well as downstream chemical upgrading. To fully support our collaborators' conversion operations projects, the ABPDU provides over a dozen downstream processing operations. Moreover, if there is a specific piece of equipment that we don't already have on site, we identify vendors from whom we can rent such capabilities. To give a sense of the breadth of equipment we can host, the italicized unit operations on this slide are those that we have rented on behalf of collaborators in the past. The ABPDU is also able to perform a wide range of analysis for process and product characterization, including chemical composition, rheology, protein analysis, and various thermochemical properties. Furthermore, being part of Lawrence Berkeley National Laboratory allows us to quickly leverage its vast array of other analytical capabilities, including those found at the Molecular Foundry, the Advanced Light Source, the Joint Genome Institute, and the Joint Bioenergy Institute, among others. For example, the ABPDU recently incorporated scanning electron microscopy, a resource at the Molecular Foundry, as part of the scope of work for a collaborator project. Collaborator engagement typically begins with an initial non-confidential discussion to understand the goals and objectives of the prospective collaborator and the general breadth of a would-be project. If the facility's capabilities and expertise appear to be a good fit, the ABPDU will offer a mutual non-disclosure agreement so that the teams can share the proprietary information needed to build a project scope. Based on that scope, the ABPDU staff drafts a granular statement of work that will include tasks and subtasks to a resolution of 4 FTE hours. Because the ABPDU is a public service, cost recovery of staff time on projects is the main driver of cost. By extension, the statement of work provides a close estimation of project cost based on the current hourly rate, which we share with the collaborator in early discussions. The iterative process of drafting the statement of work is important for establishing the scope that best suits the collaborator's objectives, and it allows for a clear understanding of the costs so that the tasks and phases are correctly prioritized. Once all parties have approved of the statement of work and its accompanying budget, we will initiate the process of drafting a work agreement. In parallel, health and safety and administrative reviews and the drafting of a material transfer agreement also take place. Multiple contracting mechanisms are available, and we are happy to go through them with you in the initial discussions. Once this phase of the contracting is complete, we are able to schedule your project on our calendar. While the contracting process typically takes about 12 weeks, if there is a compelling business case to do so, the team will do everything in its power to accelerate this timeline. For instance, Tammy Xu, a graduate student at UC Berkeley, developed a fermentation-based technology to produce biosynthetic indigo dye. The resulting company, Hue, co-founded by Tammy as its CSO and CEO Michelle Tsu, joined the IndieBio Accelerator program. In late February of 2019, Hugh reached out to the ABPDU with an immediate goal of producing enough indigo to use on an industrial dye machine and generate a prototype for their demo day scheduled in June. We not only contracted with Hugh within 6 weeks, but also generated, recovered, and delivered indigo dye within 14 weeks. The indigo you see on this industrial equipment was entirely generated via fermentation at the ABPDU. Michelle was able to showcase this prototype at IndieBio's Demo Day event.
Notion has been the centerpiece of my workflow. It's quite literally an extension of my brain.
Having worked with over 60 companies so far, our goal is to help our collaborators however we can. We started off in the biofuels and biomass space and expanded significantly into materials and chemicals. Some of our recent projects involve applications in the food, health, and agriculture sectors as well. We have also worked with many academic institutions. We have scaled up their technologies, consulted with them, and are now collaborating to solve fundamental scientific problems in process research. If you are interested in our publications, please review our work listed under the Research tab of our website. We have written support letters and co-authored proposals with companies for public funding from DOE and many other agencies. Some companies have even performed a significant amount of production at the ABPDU prior to building their own pilot plants. Often they return to us to test scaled down options as well. These activities have helped over 24 companies improve the value of their equity and accelerate the process of securing private financing, helping them to collectively raise nearly $1 billion, and in the process creating hundreds of direct and thousands of indirect jobs. Over and above this key takeaway, the ABPDU has developed or analyzed the process of numerous other companies with yet more groups deriving direct benefit by leveraging the team's expertise more broadly. We are very keen to receive feedback from our collaborators. Our inaugural Industry Listening Day offered a forum for learning exactly how the ABPDU and the Department of Energy can best support the still young biomanufacturing industry. Over 24 companies attended this event. We had a diverse group of people representing diverse companies, products, and perspectives. It was very interesting to see common themes develop among them, and we are actively addressing the issues which arose in this meeting, such as developing and providing open source virtual instrument controller software through abpdu.lbl.gov as just one example. If you have any feedback, please do share with us by writing to abpdu@lbl.gov. We are a team of about 25 members, most of whom are engineers and scale-up experts. We are always in the process of hiring, so please let us know if you or someone you know would be interested in joining the ABPDU team. To learn more, find us on the web or contact us at abpdu@lbl.gov. We look forward to scaling up with you soon. All right. So it's a little bit out of date. Some of those folks have gone on to work with some of our collaborators. That is a common occurrence. They often receive a high level of excellent training and go on to support that effort at individual companies, and we're very proud of that fact. So a little bit of outdated slide content notwithstanding, I also would like to share with you a couple of additional pieces of information about things that have been developing in terms of our capabilities. And that's true both in terms of our deconstruction and downstream processing efforts, as well as our fermentation efforts. And I will just spend a few minutes to address the fermentation side based on some information that we've recently put together. And it's the royal we. This is really Eric Sundstrom's effort. So thank you, Eric, for providing the slides and for providing all the fantastic research that you and your team have been conducting. So one of those is this off-gas capture strategy that Eric's team has put together to avoid the use of overlays in collecting various types of aviation fuel technologies that we have helped groups like Emrys, Proj, and others to pilot. And so what you're seeing here is the work that we did to scale up the technology of off-gas capture, sort of air stripping from the exhaust vent of the fermenter, and in doing so, avoiding the use of overlays, which often have real limitations just by virtue of their partition coefficients and the mere fact that materials don't always so cleanly partition into those overlays. So this process led to a really fantastic result that has allowed the teams of our collaborators to move forward with these C5 alcohol, C7 ester, and monoterpene type production efforts. In addition, gas fermentation has recently come to the ABPDU. Again, this is Eric's teams that are working on these problems where using a wide variety of different gases and the HEL technologies that we acquired, we are able to perform a variety of different kinds of gas fermentations and use in a safe fashion mixtures of carbon monoxide, hydrogen, methane, and C2H6 and other types of gases, all under pressurized aerobic fermentations. So that in order to do this, these vessels are arranged in a ventilated enclosure and are utilized under specific standard operating procedures. We are in the process, in addition to running these 500 mill reactors in the process of setting up a 20-liter vessel, and that process is moving forward nicely. So you can see that some of our collaborators on this effort include groups like Industrial Microbes, as well as Checkerspot. Groups are reaching out to us to understand how to utilize gases for their particular strains of choice, as well as to perform fermentation under pressure so that they can understand how impervious or not their strains may be to high hydrostatic pressures that they would undoubtedly experience at larger volumes. So it's a good model for scaling down these types of phenomena, and has proven its worth on a variety of fronts, not just for gas fermentation, but also just for understanding the influence of pressure itself. And with that, I will conclude. Are there any questions?
Yes, we do have two questions from Yin. The first one is, it's important to have accurate TEA/LCA modeling with innovative technologies when scaling up. So how does ABPDU support that need with every scale up project you work on?
Yeah. It varies depending upon the project. We work closely with Corinne Scown and her team at the Joint Bioenergy Institute, who has offered a variety of resources that are publicly available, and I would encourage you to seek those out. So Corinne's team is incredible at understanding TEA and utilizing these modeling tools. So that's one area that we have worked on. Another area is a little bit closer to home, and that is Ning's team, who themselves have some techno-economic analysis know-how, and in doing so, sort of collaborate with Corinne and allow us to do some sort of in-house techno-economic analysis. And then a third approach, depending upon the nature of the project, the structure of the project, we will partner with groups like the National Renewable Energy Lab, NREL, who have really been one of the juggernauts in the realm of techno-economic analysis. And so when projects involve a multi-lab collaboration, they may come into play depending upon the structure of the project. So we work closely with NREL and the Joint Bioenergy Institute, and we have some in-house capabilities for TEA, LCA as well.
Great, thanks, James. Second question is, for off-gas capture work, do you need to consider flammable quantity limitation and explosion area safety limitation?
Absolutely, and that was part of the reason why it has been kind of a very long and methodical process of ensuring that the gas fermentation work that we are doing is done in an appropriate and safe fashion. And it's, more broadly speaking, part of the reason why there's been some kind of delay and inertia in the adoption and development of gas fermentation overall. And so with groups such as the ABPDU, as well as others who have spoken today, I think it's really great to see that gas fermentation is beginning to have some resources out there kind of in the community, so that various companies, various startups, and even more developed companies that are looking for those tools can do so in a safe manner. So there are a variety of standard operating procedures and training records that we utilize in order to maintain a safe working environment for the use of these gases. Some of them obviously quite flammable and explosive under various conditions, some of them quite deadly under certain conditions. All of that has to be taken into careful account.
I don't see any more questions, but mostly comments.
Okay.
Yeah, thank you for the comments. For those who stick with us for the 12 hours of the webinar. Yeah, it's glad to know it's very useful and appreciated.
Okay, and with that, I will turn it back over to Deepti.
Thank you, James. It's been a really long day, so I'm going to keep it really quick in closing remarks. First of all, thank you, session 4 speakers and all speakers again for coming in and sharing your capabilities with our collaborators. We appreciate it very, very much. We'll be sending out a survey to everyone about what worked, what didn't. Please share your thoughts. Please share your thoughts about what else we can do to help you. This idea of Expo didn't just occur to us. We've heard about it from our collaborators in 2 industry listening days. They've asked us to connect them to scale-up facilities, and that's why we organized this event. Even if you're not our collaborator, please share your thoughts if there's anything we can do to help. We think of ourselves as a hub that helps grow the bioeconomy. We are a publicly funded institute. So if there's anything we can do, we will do our best to make it happen. And speaking of doing our best, I want to thank James Gardner, Ning Sun, and Eric Sundstrom for doing a fantastic job as hosts and Q&A monitors. Appreciate it very, very much. And special thanks to Emily Nelson and Leah Sloan. They've been doing incredible amount of work in the past 2 weeks to get 32 speakers coordinate all the presentations, make sure they are here on time. So really big thanks to them. And thank you all for being here for 12 hours. I'm guessing most of you are fermentation engineers. This is like a regular fermentation day, right? 12 hours, right? So yeah, with that, I think we will end the session here. Please do fill out the survey. We really love to hear feedback. So thank you again.
Thank you.